My name is Łukasz and this video is created for my blog Enterfa.com. Today you can see the logotype of the university I work in as an adjunct to point out that the work that I am presenting was created in Wrocław University of Technology, and I am one of the co-authors, and all authors of this work are shown at the bottom of your screen. This presentation was shown at the International Conference on Metal Structures ICMS 2016 and is about load capacity of silo that are supported discretely with skirts. If you are not familiar with terminology, in each silo there is a place where a vertical shell connects with conical hopper, and this is a hopper junction. And if you extend the silo shell below this point, or this line if you will get a skirt. And usually skirts are created simply to avoid collisions between the silo structure and supporting structure. As you can see here, if the skirt would be shorter, then the hopper would be lower, which means that its diameter on the level of the first horizontal beams will be bigger, causing a collision, so the skirt must have a certain height in this example. Also here you can see two siloses that actually have skirts, which is quite hard to see from the outside, of course. And the topic of this presentation appeared because in Eurocode, which is widely used in silo design around the world, states that if you use a skirt which is thick enough, actually 20% thicker than the silo shell at least, then you can calculate the silo as if it is uniformly supported. And since I design every silo I have shown you here, I had the stress distributions in those silos, and I knew that they actually are not uniform, that the stress is ununiformly distributed along the circumference, which means that the shell is not uniformly supported. So, with Professor Hotała and Asia Boniecka, we decided to make several calculations for one silo with the parameters listed here, simply to see how exactly skirt influences the silo capacity. And there are many parameters, of course, but for you to understand what I will be talking about, please note that each model we have created has a name which consists of two values. The first one, S, stands for skirt, and basically the higher the number, the higher the skirt. And the second one, V, stands for version, and the higher the number, the thicker the skirt. And also we've made a S1 model which was actually uniformly supported, so we have a value to compare to. If you are not familiar with numerical design methods and what all the shortcuts means, you can read about that on my blog. Here you can see that if we use a model with a relatively short skirt, its capacity is actually much lower than the capacity of silo uniformly supported on entire circumference. And in each and every slide you will see the reference values for the uniformly supported silos are given in gray fields, and below for various types of models capacities are given in certain cases. And you can see at the bottom of the slide that the capacity of the silo shell is actually almost 40% lower. If you use, even though you fulfill the criteria of Eurocode, still the capacity is much smaller than the norm would suggest. There is one point, however, that I need to mention, and that is the vertical stiffness over the column. You can see under the primary buckle in the picture on the left. those vertical stiffeners actually cause a certain concentration of stresses, which leads to a situation that the stress distribution is not uniform. But those elements are actually needed, because if there would be no vertical elements there, no stiffness whatsoever, then there would be a huge contact compressive stress between the column head and the edge of the skirt. And to avoid yielding in that zone, those vertical elements were added. If you would find a solution in which you can deal with the contact stress without adding vertical stiffening elements, then this would be a completely different story. But as far as I know, this is the mostly used solution. So if you are designing silos, please bear in mind that you should pay a lot of attention to stress distribution and when or not to treat the silo as uniformly supported. And I will get back to that idea later on. The first models actually showed what we had to show, but since we are curious in nature, we've created more models with even higher skirts, and we found out few interesting things. The first one was described already in 2007 in PhD thesis of Cornelia Derrich, and that is the phenomenon that appeared in our models with medium length skirt. If you perform a geometrically nonlinear analysis, you will notice a certain drop of load on capacity curve, which is correlated with the first buckle that appears. And if you do not understand what I am talking about, you can pause for a second and go to my blog to read about what capacity curve is and basically how this all works, so it is easier to understand what I am showing here. And the interesting fact is that numerical design requires you to use imperfections, and the capacity curve for imperfect models is a dotted line on the same chart. And you can see as the imperfections were added, this curve smoothed out, and there is no drop in capacity, which theoretically means that the capacity is actually higher because you are searching the first drop on the capacity curve, and that would be here, which is correlated with forming of secondary buckles. And as an engineer, I would say that this first buckle was actually the point where the silo met its capacity. But since there is no drop, we need to work around it somehow. And the idea I proposed in a book I wrote with a friend of mine is that when you face such a problem, it would be wise to actually measure the radial deformations in model without imperfections when the drop on the capacity curves appear, and then when you add imperfections, you can simply measure at which stage the primary buckle has radial deformation of equal value to the one obtained in analysis without imperfections. The thinking behind it is quite simple, since when we didn't use imperfections, we considered this big deformation to be failure. We can safely assume that with imperfections, the same deformation also will be failure. And if you look at the tables below, you will see that the method I propose actually nicely reduces the capacity of the silo as it should be, because obviously imperfections have a big influence on capacity. Eurocode proposes its own method, which can be considered geometrical method to estimate the capacity, and that is to measure the radial deformation in each and every rotational degree of freedom in the model, and if the rotation is higher than 0.1 radians, you can consider the model to reach its capacity. Unfortunately, in structures like silos, this rarely plays any role, as you can see that with imperfections, the value obtained from analysis with this beta, the angle equal of 0.1 radians is actually almost the same as in analysis without imperfections. And this is obvious that imperfections have influence on the capacity. So a workaround method had to be described, and my proposal is like that, to measure those radial deformations. And here you can see the capacity comparison between the models with a medium length skirt and the one that is uniformly supported on entire circumference, and still you can see that if you use the criteria I have described, the capacity is lower still, up to the point that it's actually 30% lower if you use only a bit thicker skirt than silo shell, which is usually the case. So we went even further with that, and we've discovered something even more interesting. We've noticed that if you measure the drop in capacity correlated with first buckle forming, in models with relatively short skirt, the drop is quite big. But as the skirt gets longer and longer, the drop on capacity curve is actually getting quite small, up to a point where it completely disappears. Which means that there are instances where primary buckle forms and there is no drop on capacity curve whatsoever, even in analysis without imperfections. This means that my proposal works for many models, but in some cases it's simply too little. And currently in my university we are working on an idea how to somehow describe the allowed deformations to deal with the problem. Because as an engineer I strongly believe that forming of this first buckle should be treated as capacity limit. And we need to describe somehow when to consider that the buckle actually formed. And this means also that in comparison we had to mark several models with a star because these showed the capacity with secondary buckles. And you can see an increase in capacity in many analyses between the version 1 and the version 2 and 3. This is because version 2 and 3 do not show drop on capacity curve or stability path, if you wish to call it this chart, that when the primary buckle forms. To sum this up, I would say that if you are designing a silo, you should be very aware and very precise about when to treat your shell as uniformly supported. Basically, the code states that if you are using a skirt and it's 20% thicker than the silo shell, it's okay, but reality shows that it's not always the case, and I advise certain caution when it comes to this. Also, I think that if you are using a silo that actually have a skirt to the ground, this is a textbook example of uniform support. I would still be cautious because you most likely have to cut a hole in the skirt simply to install a gate or at least a hole for a conveying machine or however you wish to discharge your silo. And those holes actually has a very strong influence on shell capacity because there will be strengthen on the edges of the hole, so on the edges of the gate, for instance, and this strengthening will be stiffer than the shell itself in that region, of course, because this will be like a hot rolled profile, for instance, or something welded there. And this would cause a stress concentration, exactly the same as the stress concentration in the vertical stiffeners over the column in the examples I have shown you, which leads in turn to a situation when a silo can lose local stability over edges of the gates. So this should be very carefully considered. when designing a silo. Also, I think that additional criteria for shell failure are needed. You know my proposal with the radial deformations. I actually use it in design. And also there are cases when it won't work, as with the last series of models. So obviously there is a lot of work to be done in that field, and I am working on it right now with friends from university. And the practical remark would be that usage of skirt as means of strengthening the shell is actually not a very good idea, because the skirt is actually a heavy part. There's a lot of steel there, and you could use this steel much more effectively if you wish to strengthen the shell. But as I show you at the beginning in the silos I have designed, usually skirts are not used as means of strengthening the silo, rather as means to avoid collisions between certain elements. And since the skirts are already there, it is actually a good idea to think about how they influence the silo capacity. But I would never use a skirt as means of strengthening the shell, because there are better ways to do that. And if you are interested in how exactly a skirt influences the capacity of the shell, there is a full text article that was printed in Proceedings for International Conference on Metal Structures, ICMS 2016. There is a book with abstracts, and also the book contains a CD-ROM disk with full versions of articles, and there we have given all the information about the design we have created. Thank you for your attention, and as always, have a nice day.